So in this question, we have a graph. So first thing we'll do is our usual Oizerga analysis. Our origin right here. So we're looking at quadrants 1 and 4. Y-axis, acceleration in normal units, and x-axis and time in normal units. So therefore, if the question is asking about acceleration or time, we'll simply read it off. The gradient is delta A over delta T, which is the rate of change in acceleration, also known as the jerk, something we don't see too often. And the area is A delta T, which has units of meters per second squared times seconds. So the area is meters per second, which is the change in velocity. So if we're asked about the velocity or change in velocity, that will come from the area. The jerk or rate of change in acceleration, the slope, or anything about acceleration and time will simply be read off the graph. So what we might just notice is that the acceleration is a constant 4, and then it shifts almost instantaneously to -2. And again, it's constant. So there's almost this discontinuity here where it shifts from 4 to 2. So we're asked to assume that it starts from rest. So V0 equals 0. We want to know the displacement of the car. Now, displacement, you'll notice, is not one of the quantities we have here. So from time 0 to time 6. So we have acceleration for a time, and we might then notice that the acceleration has an area which will give us the change in velocity. And then there is a negative acceleration, which will give us another change in velocity. So we know that V0 equals 0, and therefore, if we know the change in velocity, we can figure out the final velocity. And if we know the initial and the final velocity, we can know the average velocity. And whenever we can, we want to try to solve a problem using average velocity. So average velocity is delta x over delta t. And delta x then is average velocity times the change in time. Now we know it's 3 seconds. So we've already got 3 seconds. We just need the average velocity to know the displacement during this segment. Now we'd use a similar process here because this v and this v will be the same, which is not intuitively obvious. But what we have is an object, a body, accelerating, and then all of a sudden the acceleration shifts from being positive to negative. So it does have a velocity at that instant, which would be the same velocity here, but this area will give us a delta v. And so if we know this v, which is the same as that one, that becomes our new initial velocity, then we have a final, and we can find the average velocity. And through the same method we used above, delta x is the average velocity times the change in time, which we can see is 1, 2, 3 seconds again. So now it's a simple matter to find the area. We have a 3 by 4, so the delta velocity is 12 meters per second. So we start at 0, we end at 12, which means the average is 6. So if the average velocity is 6, that means the displacement is 18 meters. And since this is positive 4 and this is positive 3, we have a positive 12 meters per second. This is a -2 times a positive 3, which gives us an area of -6 meters. So if we have 18 meters, excuse me, this is not -6 meters, this is -6 meters per second. 2 times 6, -6 meters per second. And so far V0 was 12, and we have a change in velocity of -6. That means that the final velocity will be 6, giving us an average velocity of 9. And so that average velocity of 9 gives us a displacement of 27 meters. So in the first half, we traveled 18 meters. And in the second half, we traveled 27 meters. And 27 plus 18 is 45 meters. Now, one misconception that could come up here is the idea that since this is negative area, somehow that's negative displacement. We want to keep in mind here that if we looked at the velocity time graph, what we have is it starting at 0, increasing to 12 meters per second, and then the velocity decreases to 6 meters per second. But notice now the area of a VT graph is the displacement. Notice even after this period is over, we continue to add positive area. So the object is still moving forward even though it's slowing down. It's like a car has accelerated to its maximum and then it hits the brakes. It still continues to move forward, but it's slowing down. And that's what this represents, a negative acceleration. Second question, we've got a graph. So we have an Oy-Zerga situation. Our origin is here. So again, we are at the quadrant 1, quadrant 4 boundary. The y-axis is displacement. The x-axis is time. So therefore, we will read off the answers of any questions asking about displacement or time. The gradient delta x over delta t is the definition of average velocity, and the area x delta t has units of meter seconds, which is not any useful quantity. So there's a spring going back and forth oscillatory motion, like so, moving back and forth. The position sensor records the displacement, and there's the data. We want to know the total distance traveled by the object between 0.35 and 0.40 seconds. So let's see where that is. 0.35 seconds. There's 0.3, there's 0.4. 0.35 is about there. So maybe we might say that's 2 meters. And then 0.4 seconds is here. And that we might say is like 3.5. So minus 2 minus 3.5. So maybe we'll say that the distance traveled by the object in that time is maybe about 1.5 meters. Is what that looks like. Now we look at the choices. It's definitely not 0. It's definitely not 0. And 4 meters would be this whole thing. So it's not as much as 4. And it's certainly not more than 4. And we said 2.5. We were maybe being a little precise. But the answer is 2 meters. Centimeters. Our next question here, we have a motion dot diagram. And of course, what we know with these is that all of the delta t's are equal, because the dots are created during equal increments of time. And all of those delta t's are equal. And so the distance between them are the delta x's. So if the average velocity is delta x over delta t, then we can see here, among these first 4 dots, we might have constant velocity. And then we see what's happening is the delta x is kind of increasing, mostly, until about here. So about from this purple line through to about here. It is faster. And then clearly afterward, it slows. So definitely we have this constant period. There is some acceleration to faster, and then there's some acceleration to slowing. All right, so now we want to know toy car, the ticker tape. Time interval is 1 second. Which of the following experiments could the student have conducted to create the data shown on the ticker tape? All right, so now we have something that's kind of constant velocity, going faster and slowing down. A toy car initially increases speed, travels at constant speed, and then increases speed again. Well, this is clearly showing slowing here at the end. So there's 3 clauses to this. This could be true if we look at this as all of this is increasing speed up through there. We could look at it that way, or up to here is increasing speed. So we could, this is okay. We could okay this constant speed in here, but this is clearly false. So A is out of it. B, increases its speed. We said that was okay before. Constant speed, and then decreases speed. That is definitely true. So it looks like B is our answer. We'll consider the others. Decreases speed. Well, if we're decreasing speed, they get closer together, so that's false. And both of those are decreasing speed, false. So C and D are out. And B is our answer. Question 4. This looks like we are going to have a hit the monkey situation, which we understand what's going to happen. So the instant the dart is launched, the string is cut. So this is like the bullet being fired at the instant the monkey lets go. Positive horizontal this way and negative. And the positive vertical direction is up and negative in that direction, just like we would expect. All right, so both curves have the same, so the curves for the dart and the target each have the same slope, the same area between them and the, well, let's first analyze the graph, our Oyserga, OYXRGA. Again, we don't get confused by the question. There's our origin there. So this is positive velocities and this is negative velocities. Y-axis is velocity, x-axis is time, so therefore any questions about velocity and time will be red. The slope, delta v over delta t, is the acceleration, and which we should expect the slopes to be the same because they're both accelerating due to gravity. The area is v delta t, which would be the delta z, the vertical displacement. T0 is the function of time for the dart and for the target from T0. So that's when it's released until it hits the target. Until it hits the target. All right, so the curves for the dart and the target each have the same area between them and the horizontal axis. So what are they talking about here? So the dart has this area. And notice the values are velocity of a positive value of velocity. So velocity is some number that's large, and that number decreases to 0. The velocity equals 0 of the dart. So it's interesting. That means that it hits at exactly its highest point. The vertical velocity is 0 is its highest point. So this seems like an odd event, that you would shoot it and you would hit it when it's exactly at its highest trajectory. You know, we look at this picture, you know, the target's going to drop and the projectile is going to take this kind of shape. So the idea that this would hit at exactly its highest point, it seems very, very odd. But that's what it shows nonetheless. And the next one is the area between the graph, which is here. Now, of course, we want to keep in mind that this is a negative. The times are the same. And this is a positive. So we've got this positive value, which is shown by this grid line, and this negative value, which is shown by that grid line. It looks like they're the same values. So if this were plus 20, this would be minus 20. Target started off with a velocity of 0 and increased in magnitude. This one started off with a particular velocity and decreased in magnitude to 0. And of course, the slopes are equal because the acceleration is gravity, g minus 10. All right, so which of the following is the best method to determine the distance h from the graph? Well, distance is the area. And they're saying the target is the vertical, the h above the chart. The target is a distance h above the dart, which is what they've depicted here. So they're saying that this distance here is h. At time 0, h is the distance above the dart that the target resides. All right, so if we find the area under the curve for the dart's data, that looks like that will work. That looks like that's actually it. Twice the area under the curve for the dart's data. Well, that would be twice the height, so that's exactly false. It's exactly the wrong answer.